block floated wave. Okay, if you have such a kind of wave propagating in a periodic lattice, then the eigenvalue of the system must be a function of k. Okay, and if you were to look at this thing and solve for its eigenvalues, if you were to solve for this matrix system, for every value of k that you pick for this block floated wave, you have an eigenvalue. Okay, so you will have something that could possibly look something like this. And then it might go on and on. Okay, and then you can show that this diagram is also periodic in the k direction. It's also periodic in the k direction for this reason, that for every value of k that you pick, it could be n eigenvalues, right? Because this would be an n by n matrix. For every value of k that you pick, for a numerical method where you have n unknowns, there will be n eigenvalues. And then you just go up and up, so this curve can go on and on. Okay? But if you do a truncation, you will have only n of them, but you can make n bigger and bigger and bigger. There will be infinitely many eigenvalues for each value of k. Okay? So, but usually it's finite, and we don't calculate it to a certain value. But what I'm going to prove to you is that this function is also periodic. It repeats itself. It repeats itself after a while. You can prove that by noticing this fact that if this is my block floated wave, which is a function of k, okay, if I were to make k a periodic translation, or to give k a periodic translation, and change k by this amount, 2p pi over a. Okay, if I were to change k by this amount, what happens to my block floated wave? My block floated wave becomes e to the I kx plus this additional term that comes from the exponent, which is I 2p pi over ax, and then upx. Right? If I just translate my thing by this amount in the horizontal axis, where p is an integer, okay, p can be a positive or negative integer. Now this function is also periodic in x, right? It's also periodic in x. That is, if you make x increase by n times a, the function repeats itself. So I can lump this term with that term and call this new periodic function up tilde of x, the original periodic function, times e to the 2p pi over ax. Okay? Then this again becomes a block floated wave, right? And if I go about looking for the eigenvalue of this system, say if I were to originally look for the eigenvalue of k at this thing, and then I translate it by 2 pi over a. Okay, so this thing is actually periodic by 2 pi over a. Okay, if I move over, this is pi over a, and 2 pi over a will be over here. So it is periodic by 2 pi. If I were to move over by 2 pi over a, I will, if I originally solve the problem over here, and then if I then move over and solve the problem over here, which is k plus 2 pi over a, I end up with my assumption is the same as the beginning. I have this as my starting function. Okay, this starting function says that I still have a block locate mode, and in order to find the eigenvalue of this system at this point over here, I go through the same numerical process. I expand my UP tilde in terms of a basis set, convert into a matrix equation, and solve the same matrix equation. The matrix equation that I obtained over here at this point should be the same as the matrix equation I obtained over here. Okay, because my starting point is the same. Before that, my starting point was this. And then I use basis functions that pandas, arrive at that matrix equation. If I translate myself over by 2 pi over a over here, I get this as my starting point. I do numerical method to find this periodic function and find the eigenvalues. I found that they are actually the same equation. So the eigenvalues that I find over here must be the same as the eigenvalue that I find over here. Everybody agrees? Right? Kejun, what do you think? You agree?
Yeah, I agree, but I don't think but how do you prove that the minimum period is 2 pi over a? So
because
you only argue that after 2
pi over a,
it's the same thing,
but the minimum of this periodic function, okay, if I look at this function over here, what is the minimum p that it can have? It should be 1, right? Anything less than 1 will be 0. It can be negative, but then it's just an integer. Let's just look at positive integer. The smallest integer I can have is 1. If I translate it by only 2 pi over a, I get back the same block locate mode, block locate way. And my starting point for my numerical method is the same again. Okay, so over here, I should find the same set of eigenvalues. So if I translate by 2 pi over a, I get back the same problem. If I translate by 4 pi over a, I get back the same problem. If I translate by net mass pi over a, I get back the same problem. So this picture should repeat itself. Okay, repeat itself in this manner. I also have to prove to you that the picture is even symmetric. Okay, it's even symmetric. Okay, how do I do this proof? Well, I'm going to argue that if I were to solve this problem with plus k, if I now plug in minus k, I get back the same problem. Okay, how do I convince you of that? So if my starting point is the fact that I work with the conjugation, there are a number of ways you can argue this, okay? Let me just argue it this way to see if I can convince you that the eigenvalues, the set of eigenvalues that you get at minus k is the same as the set of eigenvalues you get at plus k. And you can easily say that if I were to start with the block locate wave that looks something like this, QPX, then the only thing that changes in this equation is IK becomes minus IK. Okay? So IK becomes minus IK, and if I go through the same process as I did before, the only change that I have is that previously I have this equation B dot A. Okay? If I were to change my k to minus k, the only change is that this equation got complex conjugated. Okay? In other words, h of minus k is just the same as h star of k. Okay, you agree? Because the only thing I did was to make this complex conjugated. And this, I'm assuming that psi m x and psi n x are real. Okay? You can also argue for the case when they're not real, but to make things simpler, I just assume that my basis functions are real. So the only complex part comes from here. Okay, the only complex part of the operator comes from there. You can easily prove that this is true. Okay, this is true. And then if this is true, then if I take the complex conjugation of this again, I get back my original equation. Assuming that A need not be real, E has been proven to be a real number. Okay. B is a real thing because B I assume to be psi m, psi n. If these are real, B would be real. And then I have this again. And this system will have exactly the same eigenvalue as the original system. Okay, they will share the same exact eigenvalue. So this picture has to be also even symmetric. Okay, it will be even symmetric. And then this is what we have as the band diagram. Okay? And you can think of this as the generalization of the tight binding model. In the tight binding model, what we have is that if we have two things, like two wells. If the electron flip-flop between these two wells, originally there was one energy level, it splits into two. Okay, and if there are many wells, three of them, and then you have three degenerate energy levels split into three. Okay, and then if you have n wells, you will have n degenerate levels split into n things. You can think of this as a splitting. Now you have one possible energy eigenvalue. You can range over a whole bunch of different k values. Okay, you can think of this as a splitting of the mode in one well. And when they couple together, they all got spread out. Okay, and then there's another mode. It's out here. They get spread out. Okay, all of this actually came from one mode, if the mode has been isolated in one well. And this is a band picture of the energy eigenstates that we have in the periodic structure. Okay, and in the tight binding model, we have this very simple picture where we have even mode or the odd mode. So even mode is in phase, odd mode is 180 degrees out of phase. So there's a very simple phase relationship 0 e to the I pi. Okay, for this is 0 phase and then e to the I 2 pi. You can think of it that way, the even mode and the odd mode. Okay. But for the block floquet mode, what it says is that the wave is traveling through the periodic lattice. There's a phase relationship between the modes of each crystal lattice. And this is the defining phase. So there are infinitely many possible phase relationships between these modes as they couple to each other. Okay, that is the generalization of this even and odd mode coupling. 0 phase, e to the I 2 pi phase, e to the I pi phase. That generalized to this e to the ikx phase. Think of them as having infinitely many wells coupling to each other, and this mode is traveling through this. Okay? And they can, of course, travel by tunneling too. The mode may get trapped here, and then they tunnel from one well to another one, and they just tunnel through this periodic lattice. Okay. Are there any questions? If not, then we can take a 5 minutes break maybe and come back for more. Okay? We can take a 5 minutes break.